We're now going to have a look at bond enthalpies, and these are quite important because they allow us to calculate, without doing an experiment, they allow us to calculate the enthalpy change of reaction. So we previously looked at that we usually have to carry out some sort of an experiment to get some data, and then from there calculate the enthalpy change of reaction, combustion, and so on. Whereas bond enthalpies allow us to do that just by having a couple of values of bond enthalpies. We can work out the enthalpy change of reaction. So firstly, let's have a look at what we mean by bond enthalpy. So bond enthalpy, or the definition that we need to know is for average bond enthalpy, is that it is the energy required to break 1 mole of a specified bond. So that's an important part there, and it must be in gaseous molecules, so it must be in the gas phase. Bond enthalpy is essentially telling us how much energy is required to break a specific type of bond. So it's telling us, how strong that bond is. The greater the bond enthalpy value, the stronger that bond is going to be. And because it's enthalpy, the units are going to be kilojoules per mole. And over here, I have a table of some average bond enthalpy values for specific bonds. So for example, the CH bond, so 1 mole of the CH bond in the gas phase has a average bond enthalpy value of 413 kilojoules per mole. And as I said, these are some more examples of different types of bonds. So for example, over here, we've got an oxygen double bonded to an oxygen. So to break both of those bonds, we require 498 kilojoules per mole of energy to break those. Okay. As you can also see, all of these values here are positive values. Okay, none of them have negative signs, so they're positive values. So that tells you that the average bond enthalpy value is always going to be endothermic. So all of these values are going to be endothermic. They should have a positive sign in front of them. These values here, you by no means need to memorize them. If you are required to use average bond enthalpy values, they will be given to you in the exam. But as you can see, we can compare strengths of bonds. So as you can see, a CH bond here is stronger than a CC bond because the bond enthalpy value for that is greater than a CC bond. Okay, so we can make comparisons of the strength of bonds by looking at their average bond enthalpy values. Okay, another thing to know is that these average bond enthalpy values are averages, okay? Clues in the name, they are not the exact bond enthalpy values. And in fact, these are actually calculated by looking at the bond enthalpy of that specific type of bond in many different types of molecules and then working out the average. So if we just focus on the CH bond, in this methane molecule over here, where we have those 4 CH bonds, each of those actually have a value, an actual bond enthalpy value of 439. When we look at a CH bond in this ethane molecule, as you can see, that value changes. And the reason it changes is because we've got a different environment over here. These CH bonds here are next to a CC bond, so that slightly changes their strength, okay? Over here, the CH bonds at the ends of the propane molecule have a different bond enthalpy to the CH bonds in the middle, again, because they're in different environments. So CH bonds, or any type of bond, is going to be different based on what type of molecule it's in, or the different types of molecules it could be in. And what they do for average bond enthalpy values, they basically just work out an average of all of these different molecules that have CH bonds, and they give you the average. So these here are not the actual bond enthalpy values, they're just an average, and therefore that can class as a limitation of using average bond enthalpy values. They're not the exact values for a specific molecule. Right, let's now have a look at how these over here actually apply to a reaction. So I've just drawn out a generic reaction. So we've got a molecule here that has 2 atoms. I've just called them atoms A. and we've got a molecule over here with 2 atoms of atom B. They start off for each molecule here, so A is bonded to A, B is bonded to B. During the reaction, something happens, and now we form new molecules. So we've got A's now bonded to B's. So during this reaction, or for any reaction to occur, we've got to have, the first thing that's got to happen is that bonds need to break. So if we look over here, the bonds that need to break are these ones over here, well, the only bonds that are actually here. So these bonds here need to break, okay? To break bonds, we need to put energy into the molecule, okay? So energy goes from the surroundings into the chemical system, and therefore bonds breaking is an endothermic process, okay? The system takes in energy from the surroundings, so we've actually got to put in energy to break this bond here and to break this bond here. Therefore, whenever we break a bond, that is classed as an endothermic process. And that's why all of these values in this table over here are endothermic, because we are talking about breaking those bonds. We're putting energy into the chemical system. So once those bonds have broken, okay, we then need to form these new bonds over here, which I've drawn in pink. So the next step that needs to happen is that bonds need to form. And this process is the opposite. When we form bonds, we actually release energy back into the surroundings. Okay, so this process here, the bonds breaking, the bonds forming process is an exothermic process. Okay, so in any reaction, we have both bonds breaking and bonds forming. And essentially, this reaction here overall is either endothermic or exothermic based on which one over here requires more energy. Okay, so if there is more energy needed to break the bonds in this reaction, the overall reaction will be endothermic. If the bonds forming release more energy than the energy taken in to break the bonds, the overall reaction will be exothermic. So depending on which one out of these two requires more energy, the overall reaction becomes either endothermic or exothermic. Right, so as I said earlier, we can work out the enthalpy change of reaction just by knowing the average bond enthalpy values. So the equation that we now need to know is this one here. So it is the the enthalpy change of reaction equals the sum, so this symbol here, which is a capital sigma, this means sum of. So it is the sum of the bond enthalpy of the reactants minus the sum of the bond enthalpy of the products. So let's now have a look at an example of a question that we could use that for. So let's just do this for the reaction of hydrogen with water, oxygen to form water. So essentially what we're doing is we're burning hydrogen to release water. I'm just going to balance this. And as we said, everything should be in the gas state. Okay, so that's when we can use average bond enthalpies. Right, so I am going to use this table on this page, so I will be referring back to that. So any values I get will just be from this table over here. So what you firstly need to do is make sure you've got a balanced equation. Okay, and I've already done that for us. I've balanced the equation. And now what you should do is you should draw out each of these molecules because you want to see the bonds in them. Okay, so we've got 2 hydrogen molecules here. Hydrogen is diatomic, so essentially it is this with 1 covalent bond between them. So they're my 2 hydrogen molecules. I've also got 1 oxygen molecule, and again you need to know that oxygen is it has a double bond in it, so make sure you draw that double bond in. And I've now formed 2 water molecules, so again just going to draw that in as well, like so. Okay, Going back to my table, I'm going to find out the bond enthalpy of hydrogen bonded to hydrogen, bond enthalpy of oxygen double bonded to oxygen, and the bond enthalpy of oxygen single bonded to hydrogen. So a hydrogen-hydrogen bond, as we can see down here, is 436. So going back to this, I've got two of those. So I've got two lots of the hydrogen-hydrogen bond. So 2 times 436. And it's got to be the sum of all the bond enthalpies in the reactant. So this is still a reactant. So it's the bond enthalpy of an oxygen double bonded to an oxygen, which is here. So that's 498. So plus 498. Okay, so I'm just going to draw a line down here to split up the products from the reactants. So this is the sum of the bond enthalpy of the reactant. So if I add that all up, I get 1,370 for my reactants. I'm going to do the same thing over at my products. So over here, as you can see, I've got 4 OH bonds. Okay, so I've got 2 OH bonds here and 2 over here. So I'm going to do 4 lots of an OH bond. So from that table, it's 464. And if I just work that out, I get 1,856. Okay, now to get my enthalpy change of reaction here, I'm going to do the sum of the bond enthalpy of the reactants minus the sum of the bond enthalpy of the products. I'm just going to minus that from that. And if I do that, I get minus 486 kilojoules per mole. Okay, that minus I got in my calculator. Okay, so when I did that one, take away this, I got minus 486. So that, I don't do anything to the sign at this point. Okay, I don't decide the sign, I just use whatever my calculator gives me. Okay, and it is the correct one because it's a combustion reaction, so we should have an exothermic reaction, and therefore a negative value here. Okay, so that is essentially how we work out the enthalpy change by using the average bond enthalpy values. I'm just going to do another one as an example. So let's do the combustion reaction of ethane. So ethane is C2H6, and if we're doing the combustion of this, complete combustion, we're reacting with oxygen, and we form CO2 and H2O. Okay, and as I said, everything should be in the gas phase if we're using average bond enthalpy values. And to balance this, we need to have 2 CO2s, 3 H2O, and 7/2 oxygen. Okay, so I'm just going to show you how we can use a fraction in this calculation. So the next step is to draw out each of these molecules. So ethane is like this. The reason you must do this step of where you draw out the molecule is because you need to see each of the bonds. If you don't do this, you are very likely to skip some of the bonds and therefore get an incorrect value in this. So we've got 1 ethane. We've got 7/2, so 3.5 lots of O2. We can't draw half a molecule, so it's just easier to do an oxygen molecule, and that whole thing there, I'm going to times that by 3.5. So whatever the value is for the oxygen double bond, I should multiply it by 3.5. We've then got 2 CO2 molecules. Again, it's important to remember CO2 has double bonds. So 2 of those molecules, and then 3 water molecules. Okay, so using that table over here, I'm just going to get the values and put them in for these. I'm just going to draw a line in the middle so we don't mix up the reactants and the products. So we're going to do the sum of the bond enthalpies of the reactants first. So as you can see, we have 6 CH bonds. Okay, so we're going to do 6 lots of the CH bond. CH is 413. And then, as you can see, we haven't accounted for this one yet. We've also got a single C bond. Okay, so that one is 347. So add 347. And then we've got our 3.5 lots of the oxygen double bonded to an oxygen. So that's 3.5 times an oxygen double bonded to an oxygen, which is 498. So if I plug this all in my calculator, I get a value of 4,568 as the sum of my bond enthalpies for the reactants. I'm now going to move over to my products. I have 4 lots of COO bonds. So I have one here, one here, one here, and one here. So I'm going to do 4 lots of the C double bonded to an O, and that's quite a high value, it's 805. And I'm going to add, as we can see, we've now got 6 lots of OH bonds. So I'm going to do 6 lots of the OH bond. So OH is 464. And if I add that all up, I get a value of 6,004. Okay, so now I've got to do the sum of the bond enthalpies of reactants minus the sum of the bond enthalpy of the products. So I'm going to do this number minus this number, and if I do that, I get my enthalpy change to be minus 1,436 kilojoules per mole. Okay, again, very important, you keep the sign that is given to you in your calculator. You don't decide the sign now. Okay. Another thing I just wanted to point out is it's another limitation of using average bond enthalpy values. As you can see, everything here, because as I said, we have to do this in the gas state, everything here is in the gas phase. Okay, and therefore what that does is it doesn't mean that this is now done under standard conditions, because if you remember, if this was to be the standard enthalpy change, everything must be in its standard state. Okay, over here, water is in the gas state, but we know that the standard state for water is actually liquid. So technically, this equation here doesn't match the definition for standard enthalpy change. So that's another limitation. And the same thing happens for this previous one that we did. We've got water in the gas phase, but we know in its standard state at room temperature and pressure, it is going to be liquid. So that's a limitation of using average bond enthalpy values, that everything must be in the gas state.